Yeah. Good evening to all of you. Now we will discuss about two more optimizers which are used for to train the machine learning model. So they are, one is the RMSprop and another one is ADAM, Adaptive Moment Estimation. So we are going to discuss about these three optimizers now in this class. So before going to discuss about RMSprop optimizer, we will discuss about the limitations of ADA-grad optimizer, which we discussed in the evening session. Someone joined, I think. Yeah. Okay. So before going to RMSprop optimizer, now we are going to discuss about limitations of the ADA-grad optimizer. So in ADA-grad optimizer, what we are doing is the model parameter is updated based on the equation gx2 plus epsilon into gx, or in other words, we will take the same equations. So model parameter m of simple linear regression model is updated as m equal to m minus eta divided by square root of capital GM2 plus epsilon into small gm, right? That means the small gm will represent the gradient of a loss function with respect to the model parameter m, whereas gm2 will represent the sum of the squares of the gradient. So the main advantage of this is it will adaptively adjust the learning rate based on the sensitivity of the model parameter on the objective function. Similarly, we are using the equation for C also. C equal to C minus eta divided by square root of capital GC2 plus epsilon into GC. Fine. Now, in the first timestamp, or in the first iteration, in the first timestamp, so the value of GM2 is equal to gradient of a loss function with respect to the modular parameter m in that iteration. Whereas in the second iteration or in the second timestamp, so GM2 is equal to, sorry, it is square, right? Square. GM2 equal to GM2 in the second iteration whole square plus gradient of a loss function in the first iteration whole square, right? Similarly, for the timestamp, so GM2 is equal to what it will be? GM3 whole square plus GM2 whole square plus GM1 whole square. That means it is the sum of the squares of the gradient. So we are adding the squares of the gradients of the previous iterations also, history information also. Like that, suppose if you run your iterative algorithm for n number of iterations, suppose if you run iterative algorithm for the n number of iterations, then at the nth iteration, the sum of the squares of the gradient expression will be like gmn that means nth iteration gradient whole square plus gm n minus 1th iteration whole square plus and so on gm in the first iteration whole square. That means we are adding the sum squares of the gradients in each iteration. In each iteration we are going to add. So for each squared gradient the weightage will be 1 into something and 1 into something and 1 into something. That means equal weightage on each squared gradient. On the gradient on each iteration has the equal weightage, that is a 1 1 1. Right? So this was happened during the iterative algorithm. That's how the capital GM2 will be updated. Right? So what is the limitation of this one is, because of adding the squares of the gradient from the starting from the initial iteration, starting from the first iteration up to the last iteration, it leads the large value of this sum of the squares of the gradient variable. It leads a large value of sum of the squares of the squared gradient. Once it becomes very large, then what will be this factor? If it becomes too large, so what will be this factor?
It will be very small.
Very small. At one instance of time, it may be approximately equal to 0 also. At some instance, it may be approximately equal to 0 also. If that happened, what will be the updation of the model parameter? What will be the updation of the model parameter in that instance?
Same as previous value, sir.
Perfect. That means your model parameter will not update. That means your model will not learn. Even though iterations are going on, but your model parameter will not update, that will not learn anything at a particular instant of time, after a particular instant of iterations. Understand? So that is the limitation of order grade optimizer. So the limitation of the order grade optimizer is, in order grade optimizer, we are using the sum of the squares of the gradient from the starting iteration to the current iteration. So when we adding all the sum of the squares of the gradient continuously, the sum of the squares of the gradient variable will be increasing, which leads the decreasing the learning rate. So once it starts decreasing the learning rate, at a particular point of iteration, the learning rate may be approximately reaches to 0 also sometimes. So if it reaches approximately equal to 0, that means your model will not update. Your model parameters will not update. That means your model will not learn anything after some time. Even though you are running the algorithm for thousands of iterations, but no use. Because gradual increasing of sum of squares of the gradient variable, the learning rate may leads towards the 0. The learning rate may leads towards the 0. That leads there is no updation of the model parameters. That means the model will not learn anything after a particular instant of time. Even though you run 1 lakhs of iterations also, there is no use. Right? So that is the main drawback or limitation of the order grade optimizer. And you have to observe one thing here is, in order grade optimizer, you are giving the equal weightage that's equal to 1 from the starting iteration to the final iteration. You have to observe that also. Because of that equal weightage, the sum of the squares of the gradient value will becomes huge value, large value, which leads the learning rate will becomes very, very small. Sometimes it may lead towards the 0. Then there is no updation of your model parameter. So to avoid this limitation, to overcome this limitation, some researchers have proposed RMSprop optimizer. So I want to tell you one thing, as I said in the previous class. After observing the limitation of the order grade optimizer, 2 researchers have started to develop some optimization algorithm to overcome the limitation of order grade. They are working simultaneously at the same time but independently, and almost both papers were published at the same time. However, both are performing well. Both algorithms are also performing well. So, but I am going to discuss about the only RMSprop, not ADA delta. Both ADA delta and RMSprop, both are developed simultaneously but independently, and both are working, and almost both are similar. Almost both are similar. So what RMSprop is doing? So what the authors who proposed the RMS optimizer, they suggested that in ADA-grad, while taking the sum of the squares of the gradient, the authors who proposed the ADA-grad, they consider the equal weightage for all the squared gradients from the starting iteration to the last iteration. As I said in the previous note board, so there is a equal weightage, that is a one coefficient for all the squares of the gradients from the starting iteration to the final iteration. But what the changes are made by the RMSprop authors is, so they have adjusted the sum of the squares of the gradients by taking the exponential decaying average. They are considered the exponential decaying average. They are considered the exponential decaying average of squared gradients. They are considered the exponential decaying average of squared gradients. So what is the benefit of considering the exponential decaying average of squared gradient is, in this methodology, when you consider the exponential decaying average of squared gradients, it leads the high weightage towards the squared gradient which are near to the current iteration, and low weightage given to the squared gradients which are in the very past iteration. Then definitely the sum will becomes very less, not similar to the your ADA-grad optimizer. I hope you understand. I will give that sentence again. So what is the main advantage of this exponential decaying average of squared gradient over the simple squared gradient is, if you consider exponential decaying average of squared gradient, so it will give the high weightage on the squared gradient which are in the current iteration and near to the current iteration, whereas it gives the low weightage to the squared gradients which are comes in the initial part of the iterative algorithm. Suppose మనం 10th iteration లో రన్ అవుతున్నాం అనుకోండి, so there is a high weightage to the gradients in the 10th iteration, 9th iteration, 8th iteration, but near current iteration, whereas low weightage to the initial iterations, that is the first iteration, second iteration, third iteration, squared gradients. So what I mean to say is, in case of the sum of the squares of the gradient GM2, then what we are doing there? So we are calculating the GMN whole square, its weight is 1, plus 1 into GMN minus 1 whole square, plus so on 1 into GM1 whole square. That means there is equal weightage from the very first iteration to the current or nth iteration, right? So which leads the gradual increasing the sum of the squares of the gradient, which leads the low learning rate, which leads the lack of machine learning model learning. So to avoid this problem, what they suggested, RMSprop authors suggested that instead of taking the sum of the squares of the gradient, just consider the exponential decaying average of squared gradients. So how it will be works is, suppose we are working on the current, suppose if you are working on the nth iteration, let us assume, then GMN whole square, it has the some high weight, whereas as it is reaches to the initial iterations, the value will be something 0.001 into GM1 whole square, like that. So the weightage on the initial weightage on the sum of square gradient in the initial iteration will be very low when compared to the weightage on the current squared gradients. So which leads because of this approach, the exponential decaying average not high as sum of squares of the gradient, right? I hope you understand, right? So ఇక్కడ ఏమంటుందంటమ్మా, సమ్ ఆఫ్ ద స్క్వేర్స్ ఆఫ్ ది గ్రేడియంట్ చేసినప్పుడు వెయిటేజ్ అన్నిటికీ ఈక్వల్ వెయిటేజ్ ఉంటుంది, కాబట్టి ఇవన్నీ యాడ్ చేసినప్పుడు ఈ వాల్యూ చాలా ఎక్కువ ఉంటుంది. అలా కాకుండా ఎక్స్పోనెన్షియల్ డీకేయింగ్ యావరేజ్ క్యాలిక్యులేషన్ ఏమవుతుందంటే, కరెంట్ ఇటరేషన్ దాని దగ్గర ఉన్న ఇటరేషన్స్కి హై వెయిటేజ్ ఉంటుంది స్క్వేర్డ్ గ్రేడియంట్లో, వేరే ఇనిషియల్ ఇటరేషన్స్లో ఆ వెయిటేజ్ అనేది చాలా తక్కువ ఉంటుంది. కాబట్టి ఈ వాల్యూ అనేది డెఫినెట్లీగా ఈ వాల్యూ కంటే చాలా తక్కువ వస్తుంది. సో ఎప్పుడైతే మనకి డినామినేటర్ తక్కువగా ఉంటుందో లెర్నింగ్ రేట్ అనేది మీకు అంత తక్కువగా జీరోకి రీచ్ అవ్వదు. ఇట్ హ్యాస్ సమ్ లెర్నింగ్ రేట్ వాల్యూ. సో మోడల్ విల్ లెర్న్ సమ్ ఇన్ఫర్మేషన్. Model will learn some information. Hope you understand, right? Fine. And now, how we calculate the exponential decaying average? How we calculate the exponential decaying average? So I will tell. So exponential decaying average will be calculated as EM2 is equal to some gamma into EM2 in the previous iteration plus 1 minus gamma into square of the current iteration gradient. Square of the current iteration gradient. So this approach you will get this type of means high weightage to the current iteration and low weightage to the initial iteration gradients, squared gradients. How it will happen we will check now. Let's assume we are in the first iteration. Then EM2 in the first iteration is equal to, generally preferable value of gamma equal to 0.9. So 0.9 into, here we are in the first iteration, right? So we have to initialize this one with 0 into 0 plus 1 minus 0.9, that's equal to 0.1 into GM in the first iteration whole square, right? So what is the value of exponential decaying average of squared gradient in the first iteration? That's equal to 0.1 into GM1 whole square, right? Perfect. Now let's assume we are in the second iteration now. So if we are in the second iteration, then what is the exponential decaying average? That is the gamma 0.9 into exponential decaying average, previous exponential decaying average. So previous exponential decaying average is this one into 0.1 into GM1 whole square, plus what else? 1 minus gamma, that is a 0.1 into gradient in the current iteration whole square. So what it will be, see, it is a 0.9 into 0.01, that is the 0.09. So that is the GM1 whole square plus 0.1 into GM2 whole square. You observe that thing. if it is a squared gradient, sum of squared gradient, then its coefficient is 1, here also 1. Coefficient of the square gradient of the second iteration, coefficient of the squared gradient of the first iteration, both are 1 here. But what happened here? It has the high weightage for the squared gradient in the current iteration, second iteration, whereas low weightage, see, it is a 0.1, it is a 0.09 on the squared gradient in the previous iteration, first iteration. So as the iterations progresses, the weightage will be further decreases for the initial iteration squared gradient, further decreases on the initial iteration squared gradient. So which leads not much high value of exponential decaying average similar to the squared gradient. So if it is not high, so definitely your learning rate, again the model will be updated like this only, m equal to m minus eta divided by, in the previous case we are considered GM2, right? And here we are considered EM2 plus epsilon, and here we are considered GM. Only thing is exponential decaying average instead of squared gradient average. So as this one is not high, similar to this one, so as it is not very high, so it will not reaches to 0, so there is no problem of it reaches to 0, and there is no problem of model stop learning, there is no problem of non-updation of the model parameters. Hope you understand, right? So only thing, the limitation in the order grade optimizer is because of the equal weightage on the sum of the squares of the gradient from very first iteration to the current iteration, which may lead large value of sum of squares of the gradient variable, which is in the denominator of the model updation parameter. Model parameter updation, right? So because it is in the denominator and it is a high value, your learning rate may reaches to 0, then model will not learn, model parameters will not update. To avoid that problem, the authors of the RMSprop optimizer, they suggested instead of taking the sum of the squares of the gradient variable, they have considered exponential decaying average squared gradient variable. So exponential decaying average of the squared gradient variable, what it will take care is, it will give high priority on the current iteration squared gradient values, and it gives the low priority, low weightage on the initial iteration squared gradient values. So because of this different weightages, so your exponential decaying average variable will not be high similar to the squared gradient variable, sum of squared gradient variable, that is the GM2. As it is not very high, EM2, that is the exponential decaying average, is not very high, so the denominator is not very high, so your this term will not reaches to 0, then there is no problem of non-updation of model parameters, there is no problem of model will not learn anything like that. Hope you understand RMSprop optimizer's exponential decaying average and how RMSprop optimizer will overcome the limitation of the RDaggrad optimizer. Now we are going to discuss about the step-by-step procedure for our RMS optimizer. Step-by-step procedure for okay, we will discuss about the RMSprop optimizer algorithm. Fine. So same, I'm going to explain the RMSprop optimizer with respect to the simple linear regression model. How that RMS optimizer will update the parameters of simple linear regression model. As it is a simple linear regression model, we have the one input XIA and one output YIA. So step 1, similar to the remaining all algorithms, step 1, you have to read the data set XIA and YIA, and you have to read your learning rate eta equal to some 0.1, and you have to read your initial values of learning parameters 1 and C minus 1, and also define number of epochs, let us assume it is 100, and also initialize number of samples in the data set, let us assume whatever it may be, and what else, anyone can, what else we have to initialize? Gamma, thank you. So we have to initialize gamma, that's equal to 0.9, and what else? Try to recollect what I said in the previous notebook.
Initial gradients.
Perfect. Not initial gradient, there is a exponential decaying average of squared gradients. That is the EM2 equal to EC2 equal to 0. If the number of model parameters increases, these variables also increases. Good. Now go to step 2. Similar to the previous one, you have to set iteration equal to 1. And go to step 3, set your sample equal to 1. Right? Now in step 4, what we have to do? Em cheyalama step 4 lo?
Gradients.
Yes, we have to calculate the gradient GM equal to, see, the gradient formula will change based on what approach you are using here. I am taking sample by sample, then your expression will be minus YIA minus M into XIA minus C into XIA. Similarly, GC equal to minus YIA minus M into XIA minus C. So these expressions will change from the approach what you are using. Are you going with sample by sample? Suppose if you are going as a batch, that means all the samples in a data set, as one batch, then your gradient will be changes. What is the gradient in that case? GM equal to minus 1 by ns sigma I equal to 1 to ns YIA minus M into XIA minus C into XIA. So this is the gradient expression if you consider a batch, complete data set as a single batch. Complete data set having the ns samples as a single batch, then you are going with this equation here instead of here. Suppose if you are using a mini batches, each mini batch contains the n number of data samples, n number of samples. Then your expression will be changed. Gm equal to minus 1 by n, not ns, 1 by n, mini batch. So n will be less than ns. It is a mini batch. So sigma I equal to 1 to ns, n yia minus m into xia minus c into xia. So this is the in case of mini batch case. Whereas the mini batch case, you have to initialize here as batch equal to 1. You have to run for batch by batch. But sample by sample, you have to run by sample by sample. But in case of the batch, if you pass all the samples as a single batch, then this complete step will not come into picture. Right? So you have to try with the different batch sizes, and you have to identify the model which is the best one based on the error matrices. So in any machine learning model, so batch size also one of the hyperparameter, like your learning rate. Learning rate is called as a hyperparameter, and gamma also called as a hyperparameter. Similarly, your batch size also hyperparameter. Number of epochs also hyperparameter. Those are the variables which will have an impact on the performance of a model. Fine, you are calculating the gradient. So what will be the step 5? What is the step 5?
EM
That's
square.
it. We have to calculate the exponential decaying average of squared gradients, that is called EM2 equal to gamma into EM2, that is the initial, plus 1 minus gamma into GM whole square. Similarly, you have to calculate the exponential decaying average with respect to the model parameter C, that is EC2 equal to gamma into EC2 plus 1 minus gamma into GC whole square. Fine. What next? So చూసారా, ఒకటి అర్థం కలిపితే మీకే ఆటోమేటిక్గా అన్ని ఈజీగా చెప్పగలుగుతున్నారు. సో వాట్ మే బి ద నెక్స్ట్ స్టెప్?
M and C, sir.
Yes. That means updation of the model parameters. So in step 6 we are going to update the model parameter, that m equal to m minus eta, that is the learning rate, divided by square root of em2, that is the exponential decaying average of squared gradient, plus epsilon into gm. Similarly, you also update c as c equal to c minus eta divided by square root of ec2 plus epsilon into gc. Right? So like that, we are going to update our model parameters of the simple linear regression model. Those are m and c. So fine. So what will be the next step? Step 7. So from here it is repeated. So only main change will come into picture in step 4, step 5 and step 6. And step 1, step 2 and up after step 7 almost are similar. So in step 7 we have to update your sample, that is called sample equal to sample plus 1. And in step 8 you have to check if your sample is less than or equal to number of samples or not. If it's true, then go to step, else go to next step. Okay, that means if you covered all the number of samples available in the data set, then you have to go to the next step. So next step is, that is called step 9, where you have to update the iteration. So iter equal to iter plus 1. In step 10 you have to check for the convergence criteria, that is number of iterations reached or not. So if iter is less than or equal to number of epochs, then go to step number, you have to tell, else go to next step. So what are the next step? That is the step 11. So here you have to read the latest m and c values, and calculate the error matrices on both training data set and also testing data set. So this will be the procedure for RMSprop optimizer. This is how RMSprop optimizer will update the model parameters. We'll update the model parameters of simple linear regression model. Hope you understand, right? Well, now tell me what will be the step here and what will be the step here. So here what will be the step?
Step 4, sir.
4. And here it is a
Step 3, sir.
step 3. That's it. Perfect. So this is the procedure for RMSprop optimizer. We will go with fast numerical calculations, and later we move to the RDM optimizer. RDM optimizer is also almost similar to the RMSprop. So we are going to discuss about the RDM optimizer later. Yeah, fine. Now we will go with our same dataset XIA and YIA. So we have the 0.2 and it is a 3.4 and it is a 0.4 and here you have a 3.8. So we have the two samples. So here step 1, read the dataset XIA and YIA and initially learning rate 0.1, gamma 0.9 and m value randomly initialize m equal to 1, c equal to -1. As it is a numerical calculation, fx equal to 1 I'm setting. And what else we have to do? We have to initialize exponential decaying average of squared gradient for the model parameter m, exponential decaying average of squared gradients of model parameter c equal to 0. Right? Oh. So ns equal to number of samples, that's equal to 2, we know. Now go to step 2, there is a set iteration equal to 1. Step 3, set sample equal to 1. Right? Now step 4, we have to calculate the gradient. So the gradient will be gm equal to minus YIA, that is the 3.4, minus m1 XIA 0.2 minus c, that is the plus 1 into 0.2. Right? So we are calculated multiple times. So this value will be equal to minus 0.84 and GC equal to minus 3.4 minus 1 into 0.2 plus 1, the value equal to minus 4.2. Right? Now after step 4 you have to go to step 5 where we are going to calculate the exponential decaying average of squared gradients, that is EM2, that's equal to gamma 0.9 into exponential decaying average of previous one, that's equal to 0 plus 1 minus gamma, that's equal to 0.1, 1 minus 0.9, 0.1 into minus gm square, right, gm square minus 0.84 whole square. Similarly, you have to calculate the exponential decaying average of squared gradient with respect to the model parameter c, that's equal to 0.9 multiplied with 0. Why 0? It is a 0. Plus 1 minus gamma 0.1 into minus 4.2 whole square. So we have to calculate these two, right? Once you get these two values, then we have to go to step 6. You have to go to step 6. In step 6, we have to update the model parameters. You have to update the model parameters. So that's equal to m equal to m minus, that is the 1 minus eta 0.1 divided by square root of em2, that is from here, plus epsilon. So we have to initialize the epsilon value, that's equal to 10 power minus 8, and here we have to use gm entam ikkada, so gm value, so that is minus 0.84 gm value. Similarly, we can update c. We can update c as c equal to c minus, that is minus 1 minus 0.1 divided by EC2 plus epsilon. EC2 will be coming from here and epsilon will be from here into GC. What is the value of GC? That's equal to minus 4.2. So minus 4.2. Right? So like that we can update the model parameters m and c. Once the model parameters m and c are completed in step 6, then go to step 7. Go to step 7, update your sample count. So sample equal to sample plus 1, that's equal to 1 plus 1, that's equal to, now we are in the current sample 2. Our sample is 2 now. Now in the step 8, you have to check for the number of samples covered or not. So if sample count less than or equal to ns, number of samples, check. Your sample count is 2 and number of samples also 2. So it's a true. If it is a true, then you go to again step 4. If it is a true, then you go to again step 4. Once you go to again the step 4, then what happened? What will be here? Minus, because we are in the second sample kada, so what will be here? 3.8. అంతే కదా, మళ్ళీ చేయను లేకపోతే ఓకే తర్వాత ఏమిటి స్టెప్ 4. now gm equal to minus yia, that is we are in the second sample, so that is 3.8. so 3.8 minus m. now this m will be from here, not this one, so this m will be from here, latest one, into xia, that is the 0.4, right, minus c. now this c will be from here, not from here, right, so into xia, that's equal to 0.4. so you have to calculate the gm, and similarly you have to calculate the gc also. so we'll calculate gc, that is equal to minus 3.8 minus m into 0.4 minus c, that you get the gm and gc. so once you get the gm and gc, now go to step 5. In step 5, what we have to do? We have to calculate the exponential decaying average of squared gradients. How we calculate the exponential decaying average of squared gradients? That is em2 equal to gamma 0.9 into, we have to take em2. so last time we are taking the em2 equal to initial value, but now it's not the initial value, we have to take the value from here. What is the value available here? You have to call that value to here. Okay, so you have to place that value plus 1 minus gamma, that is the 0.1 into gm square. so this gm will be coming from here, gm value will be coming from here. Similarly, you have to calculate exponential decaying average of squared gradient for the model parameter c. so that's equal to that's equal to 0.9 into EC2. Now EC2, don't think EC2 will be 0. No. So we have to take the latest EC2 value that will be coming from here. So we have to replace that EC2 value here plus 1 minus gamma, that is the 0.1 into GC whole square, that GC value will be coming from here. So like that we are going to update our we are going to calculate the sum of the squares of the gradient. Once the step 5 is over, then go to step 6 again. In step 6, what you have to do? Step 6. So in step 6, we are going to update the model parameters. That is m equal to m minus eta, that is the 0.1 divided by square root of exponential decaying average squared gradient with respect to model parameter m plus epsilon into gm, right? So where from each variable will come? So eta, that is the 0.1, perfect. Now this m value will be, where is the m value? That will be from the latest m value, not this one, minus square root of em2, that will be coming from here, epsilon to the 10 power minus 8, and it is the gm will be coming from this one, right? Similarly, you can update the modular parameter c also. So c equal to c minus eta divided by square root of ec2 plus epsilon into gc, ec2 plus epsilon into gc. So from where we are getting this c value? The c value will be from here, right? Not this one, okay? Minus eta, that's equal to 0.1 divided by ec2, that the ec2 will be from here, plus epsilon, that's a 10 power minus 8, into gc, so gc will be coming from here. So just replace all the values. You can easily update the model parameter M and C. Once your model parameter M and C is completed, step 6 is over, then go to step 7 again. Again step 7. So what you have to do, you have to update your sample count. Now your sample count will be, current sample is 2, 2 plus 1, that's equal to, now we have the 3. Now current sample is 3. Now check for the sample with number of samples available in the dataset. Your sample number is 3, but number of samples available in the dataset is 2. So it is a false case, right? It is a false case. Once it is a false case, you have to go to step 9. You have to go to step 9. So what you will do in the step 9? You have to update your iteration. You have to update your iteration. So in step 9, update your iteration, then iter equal to iter plus 1. Already we are in the first iteration, right? Already we are in the first iteration. So iter equal to iter plus 1 means now iter equal to 2 now. Now our iteration value equal to 2. Now what is the maximum number of iterations we set initially? That is a 1. So that means we are already reached the maximum number of iterations. Then go to next step, that is called step 11. In the step 11, just read the latest M and C values. Just read latest M and C values and calculate the mean square error and remaining error matrices on both training and testing dataset. Right? Okay. Hope you understand RMSprop optimizer. Only change is, instead of calculating simple sum of squares of the gradients, here we are going to calculate the exponential decaying average of squared gradient of the each individual model parameter. That's only the change, and remaining all are same, right? So why we are taking the exponential decaying average? Because so exponential decaying average will take care of different weightages for the different squared gradients. Like it give high weightage to the current squared gradient and low weightage to the initial squared gradients, so which leads not much high value of some exponential decaying average, which leads not high decreasing of the learning rate, which avoids high decreasing of the high learning rate, which decreases high decreasing of the learning rate similar to the ADA grade. ADA grade లో అయ్యేటట్లు సడన్గా లెర్నింగ్ రేట్ డిక్రీజ్ అవ్వకుండా ఉండడం కోసం వీఆర్ టేక్ కేర్ ఆఫ్ ఎక్స్పోనెన్షియల్ డికేయింగ్ యావరేజ్ ఇన్ ద RMSprop optimizer, right? Fine. So this is about RMSprop optimizer. Okay. Now I told in the morning, the evening previous class, so you can do some hybridization also to improve the performance. So like where it is? What happened? Okay, it's loading. Okay, finally. So I will tell the hybridization. That means you can club momentum along with RMSprop, or you can see now also we are hybridizing the stochastic gradient with RMSprop. Similar to the stochastic gradient, we are taking the sample by sample. Same approach we are hybridized to the RMSprop also. Similarly, you can hybridize momentum with RMSprop, or you can hybridize nag with RMSprop. నాగ్లో ఏం చేస్తాం గుర్తుందా? వాట్ వీఆర్ డూయింగ్ ఇన్ ద నాస్ట్రోవ్ యాక్సిలరేటెడ్ గ్రేడియంట్. సో వీఆర్ క్యాలిక్యులేటింగ్ ద గ్రేడియంట్ ఇన్ ద ఎస్టిమేటెడ్ వేరియబుల్ వాల్యూ, నాట్ కరెంట్ వేరియబుల్ వాల్యూ. బట్ RMSprop ఏం చేశాను నేను, ఐఎమ్ క్యాలిక్యులేటింగ్ ద గ్రేడియంట్ వాల్యూ ఇన్ ద కరెంట్ ఇటరేషన్ ఓన్లీ. సో యూ కెన్ ఇంక్లూడ్ దట్ టర్మ్, that is the estimated variable value you can include while calculating the gradient. So that in that way you can hybridize different models also, and you can verify how your algorithm is performing. Now we will discuss about RDM optimizer. We are going to discuss about RDM optimizer, the last optimizer for our course, that is the adaptive moment estimations, adaptive moment estimation method, right? So what is the difference between RDEM and RMSprop is, in RMSprop we have considered exponential decaying average of only squared gradient. We have considered exponential decaying average of only squared gradient. So the authors of RDEM optimizer, they suggest that in addition to calculating the exponential decaying average of the squared gradient, which represents the variance actually, variance, that is square term, also suggested exponential decaying average of only gradient, not squared gradient, that represent the mean. That is called first moment antaru danni. Square term ni second moment antaru. In stochastic environment we call it as a first moment is a mean, second moment is a variance, third moment is a something skewness and skewness. ఇంకే గుర్తుంది ఎవరికైనా? ప్రాబిలిటీలో we have the four Gaussian curve ఉంటుంది కదా. Based on the Gaussian curve there are four moments: mean, variance, second moment variance, first moment mean, and skewness, and I forget something. Okay, so here we are calculating the first moment and second moment. So by taking the exponential decaying average of the squared gradient and also by taking the exponential decaying average of the gradients. Whereas in the RMSprop, the authors of the RMSprop, they are considered gamma as 0.9, but the RDEM optimizer authors, they suggested the two new parameters called beta 1 and beta 2, and they suggested the typical values of beta 1 equal to 0.9 and the typical value of beta 2 equal to 0.999, right? And they suggest that typical value of eta, that's equal to 0.002. These are the parameters in case of the RDEM optimizer, but don't rely on these values. You can try with the different parameters. If your model performance increases, then it's good. Okay. So actually maybe some of the peoples may work with the different meta-heuristic algorithms. Suppose some researchers told that particular algorithm will perform well on a particular problem. That may not be true for your case, for your problem. So you have to try with multiple strategies. So out of which was working fine for you, then you can choose that. Okay, fine. So what the difference? Only I will go to the algorithm later. First by telling the differences in RDEM. In RDEM, we are going to calculate the exponential decaying average of gradients, not squared gradients. That's equal to beta 1 into exponential decaying average of previous gradient plus 1 minus beta 1 into GM only, because we are calculating the exponential decaying average of gradient, not squared gradient, right? Second, we have to calculate the exponential decaying average of gradient with respect to model parameter C, that's equal to beta 1 into EC plus 1 minus beta 1 into gradient of a objective function or cost function with respect to the model parameter C. So these two are called as exponential decaying average of gradients, not squared gradients, or it also called as first moment estimation. It's called first moment estimation. And similarly in the next case, we have to calculate the exponential decaying average of squared gradients also. We have to calculate the exponential decaying average of squared gradients also. That is calculated as EM2 equal to beta 2 into EM2 plus 1 minus beta 2 into GM whole square. It is similar to the RMSprop, only the parameters are changes. It is similar to the RMSprop, exponential decaying average. Only here in the previous case we are taking the gamma, now they are suggested the beta 2, right? So now it is a EC2, that's equal to beta 2 into EC2 plus 1 minus beta 2 into GC whole square. So this is called as the second moment estimation. This is called second moment estimation or variance estimation. It's called second moment estimation or variance estimation. Now, after writing these two equations, these four equations, after developing these four equations, others who proposed the Adam optimizer, they identified one more limitation, one more drawback in these four equations. What is that limitation is, at the starting stage of your iterative algorithm, what is the value of EM, what is the value of EC, what is the value of EM2, what is the value of EC2, very first iteration let us assume. We are assuming all values equal to 0 in the first step. Okay, let us assume we are in the first iteration, and in the first iteration you are going to calculate EM, EC, EM2, EC2. So while calculating all these four, we require this EM, EC, EM2 and EC2, right? So we have to initialize all these four parameters in the step 1. That is initialize the step 1 0. Fine? Hope you agree with this one, right? Now, so that's why as it is a 0, then beta 1 into this 0, 0, beta 1 into this one 0, beta 2 into this one 0, beta 2 into this one 0. So all these values are 0. Now come to the second portion. Second part. As beta 1 chosen as a 0.9 and 0.999, 0.9 and 0.999, then this term also near to 0, right? 1 minus 0.9 means it's a 0.1, and this is a 1 minus 0.999 means 0.001. That means these parameters also almost near to 0, almost near to 0. When you are multiplying this almost near 0 parameters with the GM and GM square, then what happened? This complete term also almost reaches near to 0, not exactly 0, it almost reaches near to 0, the values are near to 0. Then what happened? In the initial stage of algorithm, all the parameters are biased towards the 0. Biased towards the 0. Why? This term almost near to 0 and this term almost near to 0. So sum of these two almost near to 0. That means most of the parameters are biased towards the 0. If all the parameters are biased towards the 0, there is no proper updation, right? There is no much updation at the starting of the iterative algorithm. Then what the others have used is they have calculated they have developed two more equations. So they are called bias corrected estimations. Bias corrected estimation. So how we calculate the bias corrected estimation? That is bias corrected exponential decaying average of squared gradient represented with hat, EM hat, that's equal to EM divided by 1 minus beta 1 power t. T means iteration or timestamp. Beta 1 power t means t means iteration or timestamp. Right? Similarly, you have to calculate bias corrected exponential decaying average of model parameter C, that's equal to EC. This EM will from here and EC from here. So EC divided by 1 minus beta 1 power t. T represents the iteration. Similarly, you have to calculate exponential decaying average of bias corrected exponential decaying average of squared gradient, that's equal to EM2 divided by 1 minus beta 2 whole power t, and EC2 hat bias corrected, that's equal to EC2 divided by 1 minus beta 2 power t. So beta 2 value we know, t is the iteration, EC2 value will be coming from here, so you can easily calculate the bias corrected estimations. These are the normal estimations, non-bias corrected, and these are called as the bias corrected estimations. So maybe you ask, sir, what is the need of calculating this bias corrected? As I said in the non-bias case, so the CM value, EC value, EM2 value, EC2 value mostly biased towards the 0 at the initial case. It may be reaches to very small values. Okay. Then how we can overcome that one? By dividing with the 1 minus beta 1 power t term. Sir, what happened by adding with the 1 minus beta 1 term t? What happened here? 1 minus beta 1 power t in the first iteration, what happened? So EM hat is equal to EM divided by or 1 by 1 minus beta 1. Beta 1 entama 0.1 power t. T means we are in the first iteration. That means 0.1 power 1, 0.1. So it is a 1 minus 1 minus 0.9 power 1. That's equal to em into 1 by 0.1. That's equal to 10 into em, right? See. Now even though it is almost near to 0, but once you are multiplying with this term 10, so it will not, it restrict to move toward the 0, to bias, to restrict to bias toward the 0. That will be take care of this one. Similarly in case of em2 hat, in case of em2 hat, what happened here? So what happened? So here we are taking em2 hat equal to em2 divided by 1 minus beta 2 entama 0.999 whole power 1. So what it means? That's equal to em2 divided by 1 minus 0.999, that's equal to 0.001. That means that's equal to 1000 times of em2. So it helps us to it helps us to avoid the biasing towards the 0 at the starting iteration. Why I am telling at the starting iteration? Because at the starting iteration only the impact of this one will be exist. At the starting iteration only. As iterations are progresses ఏమవుతుందమ్మా, ఫస్ట్ అయితే ఈ టర్మ్ ఇనిషియల్ కేసు ఈ టర్మ్ ఏముంటుంది మనకు 0.9 ఉంటుంది ఫస్ట్ ఇటరేషన్లో. సెకండ్ ఇటరేషన్లో 0.9 into 0.9, that means 0.9 square. Then it will be 9981, that is 0.81. Initially it is a 0.9, then it will be 0.81. As a third iteration lo 0.9 into 0.9 ఎంత వస్తుందమ్మా 81 729, that means 0.729. See how this term, this beta 1 power t term is decreasing gradually. It is decreasing gradually. Observe 0.9, 0.89, 0.81, 0.79. So this term will be decreasing gradually. That means the impact of this one will be reduces as iterations progresses. At some time it may reaches toward the 0. Then your bias corrected value equal to non-bias corrected value, because at a later part of the iteration no need of the bias correction, because later part of your iterative algorithm these values will exist, not 0. So we require bias corrected at the initial stage only, during the starting iterations only. That's why this type of mathematical modeling is taken care by the authors who proposed the Adam optimizer. Okay. Hope you understand the Adam optimizer, how the model parameters or moments are estimated. Now we will discuss about the step-by-step procedure, how Adam optimizer will help to train our simple linear regression model having some data set xi y. Similarly, step 1, you have to initialize your data set xia yia and set eta equal to 0.1 and what else? Yeah, not 0.1. Okay, you can choose any one, but any value. Okay, here we are doing the anti-calculations, right? So I want to choose 0.1, but the authors of Adam optimizer suggested that you can take the learning rate eta equal to 0.002 and beta 1 equal to 0.9 and beta 2 equal to 0.999, and the number of epochs you have to initialize, whatever it may be, 100, and number of samples, and what else? ఎవరైనా చెప్పగలరమ్మా, what else we have to initialize? We need to initialize
em.
Yeah, so we have to calculate, you have to initialize the em, ec, em2 and ec2 equal to 0. ec2 equal to 0. I hope almost all variables are initialized. So
Epsilon.
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 Hello.
Sir, epsilon, sir.
Epsilon. What next? అసలు మర్చిపోయాను, నేను మర్చిపోయాను, మీరు చెప్పలేదు. I also forget mention. So
M and C, sir.
we have to insert the model parameters. So m equal to 1 and c equal to -1. Right. Step 2, set your iteration equal to 1. And step 3, you have to set your sample equal to 1. Now in step 4, same as remaining all, you have to calculate your gradient. As I am taking the sample by sample, your expression will be minus yia minus m into xia minus c into xia, and gc equal to minus yia minus m into xia minus c. Right? So we have to calculate the gradients. So after calculating the gradients, you have to go to step 5. In step 5, what you have to do? You have to calculate exponential decaying average of gradients and squared gradients. That is, I have to calculate em equal to beta 1 into em plus 1 minus beta 1 into gm. And you have to initialize ec equal to beta 1 into ec plus 1 minus beta 1 into gc. It's called as exponential decaying average of gradients, or we can call it as a first moment. Similarly, you can calculate exponential decaying average of squared gradient of m, that's equal to beta 2 into em2 plus 1 minus beta 2 into, here we have to take gm whole square. And again here you have to calculate ec. You have to calculate ec2 equal to beta 2 into ec2 plus 1 minus beta 2 into gc whole square. Right? Hope you are calculated the first moment or second moment, or simply call it as a exponential decaying average of gradients and squared gradients. What will be the step 6 in case of Adam? Anyone can suggest what may be the step 6 in case of Adam?
Sir, what about EM hat and EC hat?
We have to calculate in step 6, or you can include in the step 5 also. So to avoid the confusion, then it's better to include in the step 5 only. Okay, I want to include EM, EC, EM square and EC square, and also we have to calculate bias corrected all the 4 parameters. That is called EM hat, that's equal to EM. That is a part of step 5 only. Okay na? So em divided by 1 minus beta 1 power t. T means here iteration. Now, okay, not iteration, it is a timestamp. Okay, iteration will be updated only one time, but you have to update by sample also. First sample t equal to 1, second sample t equal to 2, like that. For example, I am telling I want to run this iterative algorithm for 100 times. I want to run this iterative algorithm for the 100 times. And number of samples in the data set equal to 10. Then maximum value of t will be, everyone cheppagalaru?
Sir, can you repeat again?
Perfect. I will. Let us assume I am going to run this iterative algorithm for the 100 iterations. My data set containing the 10 samples. Then maximum value of this t, timestamp equal to
10, sir. Only 10.
This t value. I will tell once again. See, this is t is not represent the iteration. You have to think that's it. So the t value will be updated for each updation. For each sample, you have to update the t value. Right? That means we are in the first iteration only. We are passing the sample 1. We are calculating the gradient. We are calculating the exponential decaying averages. I am going to calculate the bias corrected. Then t equal to 1. Right? Later we are updating the model parameter. We are not updating the iteration, but we are updating the sample 2. Now we are in the second timestamp. Then this will be 2 now. For sample 3, it will be 3 now. For sample 10, this is the 10 now. Right? Whereas in case of the iteration 2, again we start with sample 1, now it will be 11, 12, like that. Now my question is, if I am running this iterative algorithm for the 100 iterations and number of variables are 10, then how much value of t will be? Maximum value. Nth work varying
1000, sir.
1000, right? It will be varying from 1000. Okay. So andukane at latter part of the iterative algorithm, this value will be very negligible impact, because it is a 0.9 whole power 1000. If you consider only 10 samples with 100 iterations, if you go beyond that one, its value is very large. So this value will be negligibly impact on the negligible impact. Almost both are similar, because I want this impact on the initial stage only, not on the latter stage of the iterative algorithm. Fine. Okay. So similarly, you have to calculate EC hat, that's equal to EC divided by 1 minus beta 1 power t, and EM2 hat equal to EM hat 2 hat divided by 1 minus beta 2 power t, and EC2 hat equal to EC2 divided by 1 minus beta 2 power t. Okay. So I forget to ask one more question before going to steps. Now it is a step 5. In step 5, you have to calculate exponential decaying average of gradients and squared gradients, and also you have to calculate bias corrected exponential decaying average of gradients and squared gradients. That is the hat. Okay, you answered my question, that is, if I use a RMS optimizer by considering sample by sample, then maximum value of t will be 1000. If I run the algorithm 1000 times, sorry, if I run the algorithm for the 100 iterations and having the data sample 10. Okay. Now my second question is, someone I think joined. Yeah. My second question is, let's assume I have a data set having the 10 samples, and I want to run, I will write here, maybe I also forgot. Just a minute. Yeah. Fine. Yeah. So my question is, I am running the RMS optimization algorithm to train simple linear regression model for the 100 iterations. I have a training dataset having the number of samples 10. Training dataset having the number of samples 10. Okay. Now I want to consider all the 10 samples as a one batch. Okay. Then what will be the maximum value of t during the iterative algorithm, process of iterative algorithm? What is the maximum value of t?
100, sir.
Yes, perfect. It is a 100, because we are considering all the samples as a one batch. So we are updating the gradient only once over a iteration. So for one iteration 1 t value, 2 iteration 2 value, up to 100 is 100 only. One time it will be updated. Perfect. It is a 100. Now,
Sir, excuse me, sir.
Please.
Sir, I have a doubt, sir. సార్ ఇప్పుడు మనం ఈ ఈఎంస్ అప్డేట్ చేస్తాం కదా సార్, ఈఎం ఈక్వేషన్ లో బీటా 1 ఈఎం ప్లస్ 1 మైనస్ బీటా 1 జిఎం ఇస్ దిస్. ఇప్పుడు ఫస్ట్ ఇటరేషన్ అయ్యేటప్పటికి మనం ఈఎం ని 10 టైమ్స్ అప్డేట్ చేస్తాం సార్. అంటే ఈ రెకర్సివ్ ఈక్వేషన్ లో బీటా 1 ఈఎం టు ది పవర్ ఆఫ్ 10 అవుతుంది కదా ఫస్ట్ ఇటరేషన్ అయ్యేటప్పుడు 10 శాంపుల్స్ ఉంటే.
ఇక్కడ సో ఫస్ట్ ఇప్పుడు 10 టైమ్స్ వస్తుంది ఫస్ట్ టైం కి.
ఇప్పుడు ఇటరేషన్కి వెళ్ళినప్పుడు ఈఎంఐ మళ్ళీ జీరో చేస్తావా సార్, లేకపోతే ప్రీవియస్ ఇటరేషన్ లో లాస్ట్ ఈఎంఐ యూజ్ చేసుకుంటావా?
ఒక్కసారి చెప్పరా నాన్న, ఏమనుకో చెప్పండి.
సరే సార్, ఇప్పుడు ఫస్ట్ ఇటరేషన్ అయ్యేటప్పటికి ఈఎం 9 టైమ్స్ 10 టైమ్స్ అయి ఉంటుంది సార్. ఫస్ట్ ఇటరేషన్ అయ్యేటప్పటికి 10 శాంపుల్స్ ఉంటే 10 టైమ్స్ ఈఎం యూజ్ చేసుకుంటాం కదా.
ఇప్పుడు ఈ యాజ్ ఏ బ్యాచ్ తీసుకున్నప్పుడు
బ్యాచ్ సార్, మా శాంపుల్ వైజ్ కదా.
ఫైన్, శాంపుల్ వైజ్ కదా. సో ఫస్ట్ శాంపుల్ ఇది 10 టైమ్స్ అవుతుంది ఇక్కడ. EM2 EM hat ఇది
10 టైమ్స్ అవుతుంది కదా సార్.
అవునవును.
ఇప్పుడు ఇటరేషన్ అయిపోయింది, సెకండ్ ఇటరేషన్కి వెళ్ళాను అనుకోండి ఫర్ ఎగ్జాంపుల్. సెకండ్ ఇటరేషన్ లో ఈఎం ని నేను అప్డేట్ చేసేటప్పుడు బీటా వన్ ఈఎం ఉంది కదా, ఆ బీటా వన్ ఈఎం అనేది ప్రీవియస్ ఇటరేషన్ లో ఉన్న వాల్యూ తీసుకుంటామా, లేకపోతే మళ్ళీ ఈఎం అని ఇనిషియల్ గా మళ్ళీ జీరో చేసి తీసుకుంటాం?
ప్రీవియస్ ఇక్కడ ఈఎం వాల్యూ వస్తుంది కదా మనకి ఇక్కడ. ఇప్పుడు సపోజ్ ఫస్ట్ ఇటరేషన్ ఉన్నాం అనుకుందాం, సపోజ్ ఫస్ట్ ఇటరేషన్ 1 స్టెప్ 1 శాంపుల్ 1 ఉన్నాం అనుకోండి, ఇది ఎంత ఒక 0.9 వచ్చింది అనుకోండి, అది ఇక్కడ ఏమొస్తుంది 10 × 0.9 వస్తుంది. బట్ సెకండ్ శాంపుల్కి వెళ్ళినప్పుడు ఈఎం వాల్యూ ఇది తీసుకుంటాం, ఇక్కడికి వస్తుంది. ఇక్కడికి
అలా 10 శాంపిల్స్ అయిపోయినాయి సార్.
10 శాంపిల్స్ అయిపోయి ఓకే అప్డేట్ అయిపోతుంటుంది ఈఎం వాల్యూ నీకు.
ఓకే, ఇప్పుడు సెకండ్ ఇటరేషన్కి వెళ్ళినప్పుడు లాస్ట్ 10 శాంపుల్, ఫస్ట్ ఇటరేషన్ 10 శాంపుల్ ఈఎం అని తీసుకుంటాం మళ్ళీ.
సెకండ్ ఇటరేషన్ ఎండ్ ఏ వాల్యూ ఉంటుంది అదే సెకండ్ ఇటరేషన్ ఫస్ట్ శాంపుల్కి వెళ్తుంది మళ్ళీ.
ఓకే సార్.
ఓకే, so fine, someone given the right answer that the maximum value of t equal to 100. Fine. Now my question is, now I am running this RMS optimization algorithm to train simple linear regression model for the 100 iterations. I have 10 samples and I want to split the complete data set into some number of batches where the batch size equal to 2. Batch size equal to 2. Okay, batch size equal to 2. Now my question is, what will be the maximum value of t that will achieve?
500 sir.
That's 500. Yes, perfect. It is 500, right? So because batch size 2 means number of batches are 5. For each batch we have to update the t value. On what iteration? 5 batches means 5. At end of the first iteration the t value will be 5. After 100 iterations, 100 into 5, that's equal to 500. Perfect. That's it. Right, only I am asking this for understanding purpose, for clarity. Yeah, next thing, fine. Now, okay, fine. Now step 5 is over. Now step 6, what we have to do?
Update the model.
Yes, update the model parameters. So we have to update the model parameters. Step 6, we have to update the model parameters. So how we update the model parameters? That is m equal to m minus eta divided by. So they suggest that they are keeping the square root term for only exponential decaying average of squared gradients hat plus epsilon, because see under root this is some value plus a 10 power minus 8. Here what they suggest is it is under root only this e term, that is the exponential decaying average term, and they are taking the 10 power 8 outside. There is no much impact because of the small 10 power minus 8 in term. అది రూట్ లోపున అది బయట ఉన్న పెద్ద ఇంపాక్ట్ అయితే ఏమి ఉండదు. ఓన్లీ టు వై వీఆర్ యూజింగ్ దట్ 10 power minus 8 టు అవాయిడ్ దట్ నాట్ ఎ నెంబర్ ఎర్రర్ రాకుండా ఉన్న కోసం అది మాత్రం యూజ్ చేస్తున్నాం. సో యూ కెన్ కీప్ ద స్క్వేర్ రూట్ కంప్లీట్లీ. ఇన్ సమ్ పేపర్ దే ఆర్ టేకింగ్ ద స్క్వేర్ రూట్ కంప్లీట్లీ, but actually the others who proposed this RMS optimizer, they have restricted that eta to only this part only, but there is no much impact because of the small epsilon value, right? And into here we have to take a bias corrected exponential decaying average of gradient, not GM. Okay na? Here we are not taking the GM, we are taking the first moment of gradients or mean of the gradients for updating the model parameter. సో మనం ఇప్పుడు వరకు గ్రేడియంట్ మాత్రం అక్కడ కన్సిడర్ చేసాము, బట్ ఫ్రమ్ హియర్ ఇన్ ద ఆడమ్ దే సజెస్టెడ్ దట్ ద ఫస్ట్ మూమెంట్ ఆఫ్ గ్రేడియంట్ ఆర్ మీన్ ఆఫ్ ది గ్రేడియంట్స్ దే హ్యావ్ కన్సిడర్డ్ బయాస్ కరెక్టెడ్. సిమిలర్లీ సి ఈక్వల్ టు సి మైనస్ ఈటా డివైడెడ్ బై స్క్వేర్ రూట్ ఆఫ్ EC2 hat plus epsilon into EC hat. This is the denominator is we have exponential decaying average of squared gradient with respect to model parameter C, exponential decaying average of squared gradient with respect to model parameter M. But here we have the bias corrected exponential decaying average of gradient with respect to the model parameter M, bias corrected exponential decaying average of gradient with respect to C. That is the change in case of the model parameter updation. That is in the step 8. Now in the step 9, later it will be similar, right? So step 9 we have to update the sample. In step 10 we have to check with max number of samples. If it is true, that means if the number of samples less than if the current sample is less than the total number of samples, then you have to go to step 4 and calculate the gradient based on the new sample. Suppose if you cover all the number of samples in the data set, then go to the step I think 9. Update your iteration. Iter equal to iter plus 1. If your iteration reaches the maximum epochs, then go to step 11 and take the M and C values, calculate the mean square error on the training and testing data set. Suppose if you not reach the maximum number of iterations, then you have to start from step 3 again. Sample equal to 1. From there you have to start. Fine. So this is the algorithm for hello
సార్
చెప్పండి.
సార్ అక్కడ బీటా పవర్ టీ తీసుకున్నాం కదా, ఆ టీని కూడా మనం ఇంక్రిమెంట్ చేస్తూ ఉన్నాం అనుకుంటే కదా సార్.
Perfect. right. So that's why I'm telling different examples so I'm not including that. You can do that also. You have to update data t value continuously. Okay, so we have to update the t value continuously, right? What we have to do then, so we can set t value somewhere else here. Step 3 kadamma. So ఇక్కడ నేను ఒక స్టెప్ 3.2 అనుకుంటున్నా. I set t equal to 1. ఓకేనా? సో వీ హ్యావ్ టు అప్డేట్ ద t value also. ఇప్పుడు మనం అప్డేట్ చేస్తుంటాం. at end of the each sample you have to update. ఓకేనా? సో ఫస్ట్ శాంపిల్ వెళ్ళేటప్పుడు t equal to 1, సెకండ్ శాంపిల్ t equal to 2, థర్డ్ శాంపిల్ t equal to 3, 10th శాంపిల్ t equal to 10. Now iteration 2. Again first sample t equal to 11, second sample t equal to 12, like that. So we have to update the t also. Thank you Nana. So but నేను మామూలుగా వారల్గా చెప్పాను కదా, నేను ఆల్గరిథంలో ఇంక్లూడ్ చేయలేదు. బట్ వీ హ్యావ్ టు అప్డేట్ ద టీ ఆల్సో. టీ కూడా వేరీ అవుతూ ఉంటుంది, అందుకే మనము డిస్కస్ చేసాం డిఫరెంట్
స్టెప్ 3 లో సార్ t ఈక్వల్ టు 1 ఇనిషియలైజ్ చేసి
కాదు, స్టెప్ 3 తర్వాత.
కానీ ఇక్కడ ఇటరేషన్ చేంజ్ అయినప్పుడు మళ్ళీ t ఈక్వల్ టు 1 అవుతుంది కదా సార్.
గుడ్. సో అప్పుడు ఏం చేద్దాం, ఫ్లో చార్ట్ డ్రా చేద్దామా? ఫ్లో చార్ట్ డ్రా చేస్తే ఇక్కడ విల్ డ్రా సమ్ ఫ్లో చార్ట్ వేర్ వీ కెన్. సో వీ హ్యావ్ టు స్టార్ట్ సంథింగ్ అండ్ ఇనిషియలైజ్.
సార్ గ్లోబల్గా టీ ఇనిషియలైజ్ చేయొచ్చా సార్?
ఏనన్నా
గ్లోబల్గా టీ ఇనిషియలైజ్ చేయొచ్చా? స్టార్టింగ్లో టీ ఈక్వల్ టు 1,
బయట స్టార్టింగ్లో టీ ఈక్వల్ టు మనం ఇనిషియలైజ్ చేస్తే సరిపడుతుంది, ఈ లోటుకి రాకుండా. దట్ మీన్స్ ఇక్కడ ఇనిషియల్ స్టెప్లో ఇక్కడ ఆర్ బిఫోర్ ఇటరేషన్ 1, స్టెప్ 2 ముందు.
ఎస్ సార్.
ఓకేనా? సారీ. సో వీ హ్యావ్ టు ఇనిషియలైజ్ అవర్ టీ వాల్యూ బిఫోర్ స్టెప్ 2. ఓకేనా? ఆ స్టెప్ 2 కాదు, అంటే మీరు ఇనిషియలైజ్ చేసినప్పుడు ఇక్కడ టీ ఈక్వల్ 1 ఇనిషియలైజ్ చేస్తే సరిపడుతుంది కదా స్టెప్ 1లోనే.
స్టెప్ 1
అదే అప్డేట్ చేసుకుంటే సరిపడుతుంది ఇన్నర్ లూప్లో. ఇన్నర్ లూప్ అంటే ఎక్కడ? సో 2 లూప్స్ ఉన్నాయి మనకు, మీరు అబ్జర్వ్ చేశారు లేదు, 2 లూప్స్ ఉంటాయి. ఒకటి ఫర్ లూపు ఫర్ ఇటరేషన్స్ అండ్ అనదర్ ఫర్ లూపు ఫర్ శాంపిల్స్, రైట్? సో ఇక్కడ ఎండ్ లూప్ ఫర్ శాంపిల్స్ అండ్ ఇక్కడ ఎండ్ లూప్ ఫర్ ఇటరేషన్స్, రైట్? సో టీ అనేది ఇక్కడ అప్డేట్ అవ్వాలి, అంతే కదా నాన్న? అండ్ యూ హ్యావ్ టు ఇనిషియలైజ్ ద టీ ఇన్ ద స్టెప్ 1 ఇట్ సెల్ఫ్, టీ ఈక్వల్ టు 1. I think it's working well, right? While writing the program. Okay, Nana?
Yes sir.
Okay, fine. For loop equal to ఎట్లాంటి ఇది స్టెప్ 2 నన్ను మనకు, అండ్ శాంపుల్ ఈక్వల్ టు స్టార్ట్ చేస్తున్నామంటే ఫర్ లూప్ అంటే ఇది స్టెప్ 3 లాగా మనకు కదా. సో స్టెప్ 2 ముందే మనము టీ ఈక్వల్ టు 1 ఇనిషియలైజ్ చేయాలి. సో ఈ శాంపుల్ లూప్ రన్ అవుతున్నప్పుడు యూ హ్యావ్ టు అప్డేట్ ఇట్. ఇది శాంపుల్ లూప్ కావచ్చు, లేకపోతే మినీ బ్యాచ్ తీసుకుంటే బ్యాచ్ లూప్ కావచ్చు. ఇట్ మే బి ఏ బ్యాచ్ లూప్ ఆర్ శాంపుల్ లూప్. ఓకే, అదే కంప్లీట్ బ్యాచ్, మినీ బ్యాచ్ కాకుండా కంప్లీట్ బ్యాచ్ ఉందనుకోండి, ఈ టర్మే మనకు రాదు కాబట్టి టీ అనేది బిఫోర్ ఇటరేషన్సే మనకు అప్డేట్ అవుతుంటుంది. ఓకేనా? సో అదర్వైజ్ వీ విల్ డూ ది న్యూమరికల్ ప్రాబ్లమ్, దెన్ వీ విల్ సాల్వ్ ఆల్ ద డౌట్స్ దేర్. సో xi ఈక్వల్ టు అండ్ yi and it is a 0.2, 3.4 and 0.4, 3.8. Fine. Maybe ఎక్కువ టైం పట్టొచ్చు కొంచెం, బట్ వీ విల్ ట్రై. సో స్టెప్ 1 read the data set xia, yia, initialize eta equal to 0.1, and they suggest that eta equal to 0.002, okay, and beta 1 equal to 0.9 and beta 2 equal to 0.999, and most of the algorithms, machine learning algorithm, most of the machine learning frameworks, if someone new to Python and everything, they may don't know, but some people who already worked on Python, you may hear some Python libraries which are especially used for machine learning, like Keras and TensorFlow. In Keras and TensorFlow, you no need to code all those things. You can call small parameter called ADAM. If you call by ADAM, then that will run automatically. It's like a black box. So in that they have considered these parameters only. Beta 1 equal to 0.9, beta 2 equal to 0.999, and alpha equal to 0.002 as suggested by the others. అదే మీకు ఆల్గరిథం మీద ఒక కమెంట్ ఉందనుకోండి, యూ కెన్ ట్యూన్ యువర్ పారామీటర్స్. And what else? M equal to 1, C equal to -1, epochs that's equal to 1, and number of samples equal to 2, and EM equal to EC equal to EM2 equal to EC2 equal to 0, okay, and T equal to 1, okay. Step 2, iter equal to 1, step 3, sample equal to 1, iter equal to 1 and sample equal to 1, right? Now step 4, you have to calculate the gradient, right? So gradient formula మనకు ఆల్రెడీ తెలుసు కదా నాన్న, మళ్ళీ అది వేయట్లేదు ఇక్కడ. సో మనకు gradient ఎంత వస్తుంది ఇక్కడ? -0.84 and GC value -4.2. ఎందుకంటే మనం ఇదే శాంపిల్ మనం చాలాసార్లు ట్రై చేసాం కాబట్టి డైరెక్ట్ వాల్యూస్ వేసాను. Now step 5, here we have to calculate all the values like exponential decaying average of gradient with respect to model parameter m equal to beta 1, that is a 0.9, into em, initial value of em equal to 0, right? So 0, plus 1 minus beta 1, 0.1, into gm, that's equal to -0.84. Similarly, you have to calculate EC, that's equal to 0.9, initial value of EC 0, plus 1 minus beta 1, 0.1, and GC, that is a -4.2. And you have to calculate some exponential decaying average squared gradient with respect to model parameter m, that's equal to 0 beta 2, 0.999 into 0, plus 0.001, that is the 1 minus beta 2, into -0.84 whole square, okay na? And EC2 equal to 0.999 beta 2 into EC2 initial value 0, plus 0.001 into -4.2 whole square, okay. What next? We have to calculate the bias corrected values. Bias corrected values means EM hat equal to this EM value divided by 1 minus 0.9 power t అంటే 1, okay. Okay, and EC hat equal to EC divided by 1 minus 0.9 power 1, t equal to 1, right? Similarly, you can calculate EM2 hat, that's equal to EM2 divided by 1 minus beta 2, that's a 0.999 whole power t, that's a 1. And also EC2 hat equal to EC2 divided by 1 minus 0.999 whole power 1. We are calculating the bias, right? What next? Go to step 6 and update your parameters. So మనకి వాల్యూస్ రీప్లేస్ చేయడం అమ్మా, జస్ట్ ఏంటి EC2 అంటే ఎక్కడ ఉంది, it will come from here, EC2, and EM2 coming from here, and EM value will be coming from here, and EC value will be coming from here, okay. All values are available, just replace it. So So you can calculate all the parameters, all the bias corrected exponential decaying averages. In step 6, what you have to do? Update the parameter. So m equal to m minus m అంటే ఏమొస్తుంది ఇక్కడ
1 sir.
1 minus eta, that is the 0.1 divided by square root of bias corrected exponential decaying average of squared gradient with respect to the model parameter m plus epsilon, that is the 10 power minus 8. This one will be coming from ఇది ఇక్కడ ఉంది కదా, సో ఈ వాల్యూ ఇక్కడ రీప్లేస్ చేస్తారు ఇంటూ హియర్ ఇక్కడ ఏమొస్తుందమ్మా ఈఎం హ్యాట్. దిస్ ఈఎం హ్యాట్ విల్ బి కమింగ్ ఫ్రమ్ హియర్. ఓకే, and this term em hat square, that is em2 hat, that will be from here. Similarly update the c equal to c minus, that is c anta minus 1 kada, so minus 1 minus 0.1 divided by square root of ec2 hat plus epsilon into ec hat. This ec hat will be coming from here and ec2 hat coming from, sorry, ec2 hat coming from here and ec hat will be coming from here. All values are available, just replace it, update the parameter. Now here we have to take step 7, we have to update t value, t equal to t plus 1. Update the t value because we are going to next sample, right? We are going to next sample. Now again in the step 8, update the sample. Rest of things are same, right? ఒక్క స్టెప్పే మూవ్ అవుతుంటుందమ్మా ముందుకి. ఈ స్టెప్ 7 ఒకటి కొత్తగా వచ్చింది మనకు. ఓన్లీ స్టెప్ 7 is coming into the picture because of this t value. Because of this t value, this will come. So 7 ఇది అవుతుంది, 8 ఏంటి? Step 8 is updating the sample, that is the sample equal to sample plus 1. And step 9 ఏమవుతుంది? Compare the sample number with maximum number of samples available. Compare the sample number with maximum number of samples available. So if all the samples are covered, then you go to the next step where you have to update the iteration. If all samples are not covered, then you go to a step amma?
Step 4.
Step 4. Okay, we are going to step 4. Let us assume all the samples are covered. Then update the iteration, iter equal to iter plus 1. Now check for the another convergence, that is if iteration reaches the maximum number of iterations or not. If it not reaches the maximum number of iteration, then we are going to
Step 3.
Step 3, right? We are going to step 3. If all number of iterations are reached, then just read the m and c values and calculate all the errors, right? So this is the how we are doing the. Now ఇప్పుడు clarity వచ్చిందన్న, how we can update the t value. Okay na? Is it fine with respect to t parameter in the algorithm? Yes, someone we have a discussion, right? Where we can keep the t and how it will be updated. Is it fine?
Yes, sir.
Okay, thank you. So fine, right? So these are the algorithms generally we are using in the machine learning for the training purpose, training of the machine learning model. If you understand all the algorithms from the stochastic gradient to the ADAM, you can apply the same approach. What type of model you want to use, you can use. Later, if you are able to do any modifications for the improvement, that's very better if possible. You can work in that direction also if required. But if you are in the electrical engineering domain, if you are able to modify the algorithm, it's very interesting. Whereas some people may use the metaheuristic techniques also to update these parameters nowadays. But actually in the application point of view, in the real-time application point of view, nowadays if you want to use the machine learning models for the real-time application, they are using all these conventional approaches only, like stochastic gradient, batch gradient, MBGD, momentum, ADAM, RMSprop, all these algorithms only using for the real-time applications. So if you understand all the algorithms, if you are able to write your own code, it will help you to improve your confidence. However, really, if you want to develop an application based on the machine learning model, so I think that knowledge of this complete algorithm, step-by-step knowledge of the algorithm is not required if you want to only application develop point of view. But if you want to learn something beyond that one, these all are required. ఎందుకు అవసరం లేదు అంటున్నానంటే ఆల్రెడీ సమ్ ప్రీ ఎగ్జిస్టింగ్ లైబ్రరీస్ ఆర్ అవైలబుల్ ఇన్ ద పైథాన్, లైక్ keras and TensorFlow. So what we have to do is just we will call those libraries. Just we will call those. I will show one Python code to you. Give me time. Similar to the Google Colab, there is a Microsoft cloud service that is called Azure Notebook. Microsoft Azure Notebook. So you can use Microsoft Azure Notebook also instead of Google Colab. Of course, you have to create a Microsoft account for that one, because most of the participants have the Gmail account, so that I tried with the Google Colab. Just a minute అన్న, ఆ కోడ్ మీకు చూపించి ఈరోజు క్లోజ్ చేద్దాము.
సార్
చెప్పండి అన్న.
సార్ యాక్చువల్గా స్టార్టింగ్ స్టోకాస్టిక్ గ్రేడియంట్ డిసైన్ నుంచి ఇక్కడ లాస్ట్ యాడమ్ ఆప్టిమైజర్ కి వచ్చేవారికి నంబర్ ఆఫ్ ఇనిషియల్ పారామీటర్స్ అనేవి ఇంక్రీజ్ అవుతున్నాయి కదా సార్?
అవును అవును.
ఐ మీన్ మనం ర్యాండమ్ గా చూజ్ చేసుకునేవి.
అవునవును.
సో అది డ్రాబ్యాక్ అవుదా సార్?
ఓకే, ఐ విల్ టెల్. జస్ట్ అర్థమైంది. మీరు కూర్చొని అర్థమైంది. ఒక్క నిమిషం నాకు టైం ఇవ్వండి. ఇక్కడ అర్థం చేశారు ఇక్కడ నాన్న. ఆర్ ఏబుల్ టు సీ ది స్క్రీన్? మళ్ళీ కంట్రోల్లో వస్తుందో లేదో నాకు తెలియదు. ఒకసారి ఇట్స్ వర్కింగ్. ఇక్కడ అబ్జర్వ్ చేశారా? ఆర్డర్ డెల్టా విత్ ఇన్ ద బ్రాకెట్. అంటే వెనక ఏం జరుగుతుందో మనకు తెలియదు. Just you can call with that name, or you can call the optimizer with that name. That's enough. It will take care of remaining all those things. సో కానీ బ్యాక్ ఎండ్లో జరిగేది ఏమంటుందంటే, మనం ఇప్పుడు ఏమైతే డిస్కస్ చేస్తున్నామో అటువంటి ఆస్పెక్టే బ్యాక్ ఎండ్లో జరుగుతుంటుంది. బట్ నేను యాజ్ ఓన్లీ అప్లికేషన్ డెవలప్ చేయాలనుకోండి, సో నో నీడ్ టు రైట్ దట్ అమౌంట్ ఆఫ్ కోడ్ అగైన్, రైట్? ఆల్రెడీ లైబ్రరీస్ ఆర్ అవైలబుల్ ఇన్ ద పైథాన్. జస్ట్ కాల్ దట్ మెథడ్ by using its name, like order delta or ADAM or RMSprop or momentum. Just you can call optimizer.keras.optimizer.order delta or keras.optimizer.ADAM. So it will take the code of the ADAM which is available in the backend, it will run. Okay, అర్థమవుతున్నాను. బట్ అదే మనకు ఫస్ట్ టైం అనుకోండి, వీ డోంట్ నో వాట్ హ్యాపెన్ బిహైండ్. బట్ మీకైతే ఒక క్లారిటీ ఉంటుంది కదా. జస్ట్ వీ హ్యావ్ అన్ ఐడియా వాట్ హ్యాపెన్ బిహైండ్ అండ్ వాట్ వీ క్యాన్ డూ ఫర్దర్. ఒక క్వశ్చన్ అడిగారు. దట్స్ నైస్. when we are moving from SGD to ADAM, the number of parameters are increases. But the main criteria that what we considered in case of any application or any project is at how much good accuracy the model is predicting. That is the primary focus for us. Okay, whereas number of parameters which required more memory space, and also as the number of parameters increases, it may have more number of equations, required more computation. నాన్న, మీరు ఎవరో క్వశ్చన్ అడిగారు కదా, పేరెంట్ చెప్తారు ఒకసారి. రఘువంశీ గారు. సో నెంబర్ ఆఫ్ పారామీటర్స్ మనకు ఇంక్రీజ్ అయ్యేటప్పుడు, సో మనకు 2 డ్రాబ్యాక్స్ ఏంటి అంటే, నెంబర్ ఆఫ్ పారామీటర్స్ ఇంక్రీజ్ అయితే డెఫినెట్లీగా వీ రిక్వైర్
Memory.
మోర్ కంప్యూటేషన్స్ కావాలి కదా. సో
Yes, sir.
యూ రిక్వైర్డ్ ఏ హై కంప్యూటింగ్ పవర్ మిషన్స్ కావాలి.
Yes,
రెండోది ఆ పారామీటర్స్ రన్ చేస్తున్నప్పుడు యూ హ్యావ్ టు స్టోర్ ద వేరియబుల్స్ ఆల్సో, వాల్యూస్ ఆఫ్ ది వేరియబుల్స్ ఆల్సో మనం స్టోర్ చేస్తుంటుంది రన్ టైంలో. వీ రిక్వైర్డ్
Yes,
మెమరీ
so memory ఎక్కువ.
ఆల్సో. బట్ నౌ డేస్
ఇప్పుడు
because of availability of
Yes,
the
sir.
high-end computers, because of
Yes,
the
sir.
availability of the high-end computers, the memory space and the computation speed is not a primary criteria. The primary criteria is the most sophisticated and robust model, accurate model. So for that, even
Yes,
the
sir.
number of parameters increases, if you are achieving the good model, then it's a better.
ఓకే
Right?
సార్ ఇప్పుడు
And moreover-
ఫర్ ఎగ్జాంపుల్ సార్ సార్ ఫర్ ఎగ్జాంపుల్ ఒక అప్లికేషన్ ఒక 50 శాంపుల్స్ కి నేను ఈ అల్గోరిథం రన్ చేసి ఫైనల్ గా ఒక పారామీటర్స్ ఫిక్స్ చేశాను సార్.
Hmm.
సేమ్ అవే పారామీటర్స్ ని అవే వాల్యూస్ ని వేరే అదర్ అప్లికేషన్ లో ఐ మీన్ వేరే శాంపుల్స్ ఇస్తే సార్
వర్కౌట్ అవ్వదు కదా.
అదే
Example
సార్.
ఏంటంటే ఇప్పుడు సపోజ్ ఏనన్నా ఎగ్జాంపుల్ ఇది మనం సపోజ్ రఘు, నేను
Yes, sir.
ఫస్ట్ ఇయర్లో ఎలక్ట్రికల్ సబ్జెక్టు చదువుకున్నాను. సో నా బ్రెయిన్
Yes, sir.
బాగా ట్రైన్ అయ్యింది దానికి. సో ఎలక్ట్రికల్ సబ్జెక్ట్లో ఎగ్జామ్ పెడితే నేను బాగానే పెర్ఫామ్ చేస్తా. నేను బాగా ట్రైన్
Yes,
అయ్యాను,
sir.
ఈఎంటీ పేపర్ ఇచ్చారనుకోండి సెట్ అవ్వదు కదా.
అదే
సో
Yes, sir.
దట్ విల్ బి చేంజెస్. దట్ వే మనకు మోడల్ టు మోడల్, ప్రాబ్లమ్ టు ప్రాబ్లమ్ వీ హ్యావ్ టు ట్రైన్ ద మోడల్.
అదే వన్స్ అగైన్ ఆ పారామీటర్స్ మనం చేంజ్ చేసుకోవాలి.
సో అఫ్ కోర్స్ మనం మిషన్ లెర్నింగ్ మోడల్ డెవలప్ చేసామంటే స్పెసిఫిక్ ప్రాబ్లమ్కి మనం చేస్తాం కదా. స్పెసిఫిక్ ప్రాబ్లమ్ అంటే సపోజ్
Yes.
ఫోర్కాస్టింగ్ ప్రాబ్లమ్ అనుకోండి, లోడ్ డేటాకి మీరు ట్రైన్ చేస్తారు. అదే విండ్ ప్రాబ్లమ్ అనుకోండి, విండ్
Yes,
డేటాకి
sir.
ట్రైన్ చేస్తారు. అలానే లోడ్ డేటాకి ట్రైన్
Okay.
చేసిన మోడల్ విండ్ డేటాకి వర్కౌట్ అవ్వదు.
Yes, sir.
Okay. Okay, fine. So this is how we can call the optimizers. So like the optimizers మనం యూజ్ చేయాలి అనుకుంటే నో నీడ్ ఆఫ్ ఆల్ దీస్ ఫండమెంటల్ ఇన్ఫర్మేషన్, బట్ మనం తెలుసుకోవాలి యాజ్ ఎ రీసెర్చర్స్. మనం తెలుసుకొని మనం యూజ్ చేస్తే ఇట్ విల్ బీ వెరీ గుడ్. అదర్వైజ్ ఆల్సో యూ కెన్ కాల్ ద యూజింగ్ ద లైబ్రరీస్ యూ కెన్ కాల్ ద ఆప్టిమైజర్స్. ఓకేనా? సో మామూలుగా జనరల్గా మేబీ మా రెడ్డి ఎవరైనా ఉంటారు సాఫ్ట్వేర్లో వర్క్ చేస్తున్న వాళ్ళకి ఏంటంటే మెయిన్ అప్లికేషన్ డెవలప్ చేయాలి. సో ఇఫ్ యూ వాంట్ టు డెవలప్ ద అప్లికేషన్ యూ కెన్ యూజ్ ద లైబ్రరీస్. మీరు ఎట్లా చేస్తారనేది సెకండరీ కదా. సో వెదర్ యువర్ అప్లికేషన్ ఈజ్ వర్కింగ్ ఫైన్ ఆర్ నాట్, దట్ ద ప్రైమరీ క్రైటీరియా. ఓకే, బట్ యాజ్ ఎ రీసెర్చర్, యాజ్ ఎ స్టూడెంట్గా స్టార్ట్ చేసేటప్పుడు కానీ రీసెర్చ్ కానీ అదే ఫ్యాకల్టీగా ఉండేటప్పుడు మాత్రం ఇట్స్ బెటర్ టు నో వాట్ హ్యాపెన్ బిహైండ్. ఆ తర్వాత మీరు అది యూజ్ చేస్తారా లేదనే తర్వాత సంగతి, బట్ యూ హ్యావ్ టు నో వాట్ హ్యాపెన్ బిహైండ్. లేకపోతే అంత బ్లాక్ బాక్స్ లాగా ఉంటుంది. వీఆర్ ఫీడింగ్ సంథింగ్, ఇట్ ఇస్ గివింగ్ సంథింగ్, దట్స్ ఇట్. ఓకేనా? సో ఫర్ టుడే ఐ వాంట్ టు క్లోజ్ ద సెషన్. So all the theory aspects and numerical computations are completed, whereas tomorrow we will discuss on the labs based on RDM and RMSprop and what else remaining in our case. Okay, Nana? So I want to close the session for today and we will meet tomorrow at 7 p.m. Thank you.